Hello everyone, my name is Zheng Hui from the University of Delaware. Here I want to talk about our paper, Markov Parallel Tracking and Mapping for Probabilistic SLAM. The motivation of this work is straightforward. We want to efficiently solve SLAM problem, and at the same time, we want to guarantee the accuracy of the state estimation. So for this purpose, in this paper, we propose an efficient SLAM estimator that performs parallel optimization. Especially in our estimator design, the Markov assumption of probabilistic SLAM is always followed in order to improve the accuracy. The most related work to this paper is a method called parallel tracking and mapping. The basic idea of this method is to split a SLAM process into two pipelines, which can be run in parallel, for example, on a multi-core processor. And those two pipelines estimate different set of states using different set of measurements. And usually it can be realized by a front-end and a back-end. In the front-end, usually the sliding window odometry is used to provide an immediate estimate for the most recent state. And when loop closure is detected, relocalization is also performed in this pipeline. While for the backend, usually boundary adjustment is formed to optimize a subset of the past state, usually called keyframe. And one popular approach to realize it is the post graph, which only cares about the poses of the keyframe. And there are several well-known algorithms that realize such framework. For example, ArcSLAM, LSD-SLAM with their visual-inertial versions, and also Lens model. So here let's briefly go through the formulation of SLAM problem. So usually we can summarize what we want to estimate in SLAM into a state vector, which usually include the poses of the robot and its observed features at every timestamp. However, in practice, those states are not directly observable, so we have to infer their values based from the noisy sensor measurement, which are usually modeled as a probabilistic constraint. And also, we can have some prior knowledge about the environment, for example, from the initialization. And with the measurement together, we can formulate a posterior distribution for the state based on the Bayesian theorem. And this posterior distribution is sufficient to represent, to describe the SLAM process is because the Markov assumption, which emphasizes that the SLAM state should be a complete summary about the history of the robot. So with this posterior PDF, we can find the optimal state estimate by maximizing it, which is called maximum posterior estimate, and which can be equivalently solved as a minimization problem. While considering that the measurement models are usually non-linear, so in practice, we actually solve a linearized problem. So here, instead of directly finding the optimal state estimate, we prefer to find the optimal correction to the current state estimate. And we can further utilize the square root of covariance matrix to convert this problem into a linear least square form, which is called square root information form. And under this form, we can efficiently perform update using QR factorization. And with the updated information factor, we can further solve optimal state correction using back substitution. And based on our previous introduction, here I want to point out the issue that the PTAM-based method has. The first one is about the front end. So here the loop closure measurement is used for relocalization. However, because we do marginalization, the front end actually has no information about the past state that correspond to those loop closure measurement. So as a result, the front end has to assume those past states as perfectly known, and which may easily lead to overconfident or even biased state estimate, which is known as the inconsistency issue. The other one is about the backend. So the global optimization only includes a subset of the past state and usually performed at a low frequency. So this means the new incoming state will have no chance to be jointly optimized, and this is known as the joint optimality issue. And we can notice that both issues are due to the incomplete state vector in the front end and back end when loop closure occurs. So in order to overcome those issues, we propose our Markov solution, MPTAM. So here, because the front end has no information about any past state, so our front end will no longer do relocalization. So instead, the loop closure measurement will be used for global optimization in the backend, where we will have sufficient information about both past state and current state. So in this way, the state vector of the front end and backend will be complete for processing their respective measurements. So for implementation, we implement our front end as a sliding window estimator, which will only estimate the most recent state and keep marginalizing the past state in order to bound the size of the problem, so which is shown as in figure 5. And here we should note that the front end is only used for providing immediate state estimate. So actually it can be realized by different sliding window estimators. For example, the following open source algorithms including OKWith, RView, and OpenWinds. Well, for the backend, we will perform incremental batch optimization, which will include both past state and current state. According to figure 6, here we want to divide its information factor into two parts. The upper part, which will be used for tracking the information of the most current state, will be updated in real time, while the lower part, which is only about the past state, will be updated at a relatively lower speed. And here we have two cases for the backend, depending on the occurrence of loop closure. So when there is no loop closure, we will only do information augmentation. Well, once loop closure is detected, it will trigger global optimization. For information augmentation, actually what we need to do is first update the upper part with the incoming measurement. Well, here for the remaining measurement factor after update, we will directly discard it in order to improve the efficiency. And then we will augment the lower part with the information factor that corresponds to the state being marginalized by the front end. And then once we found loop closure, then we will perform global optimization. So here, similar as the information augmentation, we will first update the upper part with the incoming measurement, including loop closure measurement. Well, in contrast to that, here the remaining measurement factor will be further factorized by the lower part in order to solve for the correction of the past state. And here we should note that when we perform update in the lower part, actually the upper part can still be updated by the new incoming measurement. And once we have the correction for the past state, we can then substitute it into the upper part to further solve the correction for the current state. So in this way, the front-end estimate is also jointly optimized by the global optimization. We further implement our visual-inertial SLAM system to validate our method. And here we compare it with the one of state-of-the-art WINS model. Two challenge datasets are used for evaluation. The first is the benchmark York dataset, and the second is the challenging long-term multi-loops dataset. And based on our result, we can find that our MPTAM achieve better front-end accuracy with the global optimization. So this can be seen from the table 1. So here, after we enable loop closure correction, the front-end accuracy is improved for all the sequence in the York dataset. And we should note that the processing speed of the front-end is still very fast. Second, the loop closing accuracy can be accurate even with some approximation. And this can be seen from the figure 9 and table 2. So here we want to improve the efficiency of the backend by approximating the information matrix of the backend as a diagonal banded matrix. So here we can see that even with such kind of approximation, we still achieve better accuracy by having less number of loop closure correction as compared to WINS model. So at the end, we want to summarize the properties of our proposed MPTAM estimator here. So first, it returns the advantage of processing in order for the efficiency, and it follows the Markov assumption of probabilistic SLAM in order to improve the accuracy. And also, different sliding window estimator can be used for realizing the front end, which demonstrate its versatility. And although the backend is able to be run at a lower frequency, we can also improve its efficiency by using some conservative approximation. So that's all the content in my report. Thank you for listening, and if you have any question, please feel free to ask me.